My YouTube debut's not started well, but anyway. So I'm Dan Lee, and I'm gonna talk to you about hybrid ensemble variational data assimilation and a high resolution global ocean model. And so, quick introduction. So, the Met Office Global Ocean Forecasting System, FOAM, has produced daily operational ocean forecasts for many years. So FOAM uses the NEMO model and the NEMO VAR assimilation system, running 3D VAR, assimilating long track sea level anomaly, swath sea surface temperature, profile temperature and salinity, and sea ice concentration. The system is also used to generate ocean-only forecasts and as part of the coupled numerical weather prediction system. So we did some work on Ensemble DA before, and we have a paper, Lea et al. 2022, and we developed a foam-based ensemble system and tested hybrid ensemble variational data assimilation. And we found that compared to 3D VAR, this gave a significant improvement in the ocean DA performance. The problem was that it does come with a big cost requirement to do ensemble DA. I mean, for one thing, running the ensemble is expensive because you have to run the system multiple times, the models multiple times, and then the other thing is that the data assimilation also, the cost also goes up for that. And previously it wasn't feasible for it to go operational for running operational forecasts, but we now do have the resources to do that. So meanwhile, the system itself has evolved. So there's been updates to the global ocean model from GO6 to GOSI9. There's also been improvements to the 3D VAR data simulation and an increase in the model resolution from 1/4 degree to 1/12 degree. And these plots that I'm showing here are just showing the improvement from the GO6 version to the GOSI9 version, including the data simulation improvements. So substantial reduction in the temperature profile error, RMS errors, and similarly for the sea level anomaly. And so the worry is just we were seeing similar improvements from Ensemble DA, and so will we be able to still benefit from doing it as we did previously? So that's the question. And so just a bit more about the system, because I'm going to do a talk about it. You can assume that it did still improve things, but anyway. So this system is an ensemble of separate data simulations, but we can use the information from the different ensemble members in the DA step. So we have, for the 12th degree system, you have a 12th degree NEMO observation operator run, and then that is fed into a NEMO VAR, feed the background and the innovations into NEMO VAR running at 1/4 degree, and then those increments are applied to the 12th degree NEMO. And then we have 36 perturbed members with forcing from the Met Office atmosphere ensemble. So the ensemble is at a 20 kilometer resolution. For the deterministic, the unperturbed member, it's at 10 kilometers. So we have observation, position and value, and model perturbation schemes. And we use a RTPS balance respecting ensemble inflation. And we use hybrid ensemble variational DA. I'll talk about that a little bit more shortly. For most of the testing for now, we're not going to actually show results for the 12th degree. We'll stick to the 1/4 degree just because it's quicker for development. So the 12th degree takes about 30 times the HPC resources for the model run. So we just talk about the model perturbation scheme a little bit more. So this uses the Storto et al. Scheme, and it covers a lot of aspects of the model uncertainty. So many things, parameters to tune. So it has the stochastic parameter perturbations, so deal with parameter uncertainty, and then stochastic perturbed parameterization tendencies to deal with tendency issues in the model, and then there's a stochastic energy backscatter scheme to represent the missing subgrid scale variability. We used this scheme in the old version. We made a few updates to it, partly because some of the settings didn't work anymore with the new model, It's always dangerous to perturb models because their stability can be quite sensitive to the parameter settings. So one of the big new things is the use of bulk formulae parameter perturbation. So that's air, sea drag, sensible heat, and evaporation. And so that we think that's made a big difference to the old system in producing quite strong surface perturbations, particularly for SST. So just show these plots just show a few examples for different variables of the impact of on the ensemble on a free running ensemble of making those perturbations. And you can see this was in Northern Hemisphere winter, so you can see in the Southern Hemisphere there's a really strong SST spread that's been added, and quite a lot's going on in the tropics and in the other variables. So now we'll talk about the data assimilation. So this is a hybrid ensemble variational data assimilation, and it uses ensemble-based background error covariance. So you can create a background error estimate based on ensemble perturbations, and you do need to localize that for a normal ensemble to reduce the sampling errors at large distances. And in our case, we use 2 times the Rossby radius with a 100-kilometer cap. And then the other aspect for stabilizing this as well is that you do hybrid DA, where the background is a weighted sum of the standard model background error, the 3D VAR background, and the ensemble-based background. And so we did some work in Lea et al. 2022 where we showed that there was optimal settings for the hybrid weights. So if you just do standard 3D VAR, the sea level anomaly errors increase, and then as you increase the hybridization, the amount of ensemble base, then the errors drop, and then they tend to rise again if you do just a pure ensemble. So there's a kind of optimal hybrid weight, and we've chosen for this work to just do a 50-50 weight on the modeled background error and the ensemble based background error. So you can also use these set of idealized observations where they're widely spaced so that each observation's increments don't overlap with the other observations. And in this case, we're using sea level anomaly observations with a positive innovation, and this helps to explore the error covariance structures, and we use it to tune the hybrid weights and the localization length scales, and also to test the impact of the ensemble size. So for the 5 panels on the left, you've got the background temperature as a vertical section, then the spread of the ensemble, and it shows below that, it shows some example increments for the 3D VAR case, then a hybrid case, and then a full ensemble case. And you can see that as lots more structures develop, although whether as you move away from the observation location itself, whether some of those are genuine structures or noise is a question. And then on the right hand side, there's 3 panels, and in that case we're showing the impact of changing the number of ensemble members on these increments from 4 to 18 to 36, and the conclusion there is that we're getting reasonable convergence with the 36 for our localization length scales, etc., with the 36 members. So that's quite encouraging. And now a busy slide with a lot of results. So we've run the system for 1 year, and this is the quarter degree with the quarter degree NEMO and quarter degree data assimilation. And the conclusion of this is that we do still see a very big improvement with the hybrid DA. So this time series of the sea level anomaly, it goes from 6.3 centimeters, 5.1 centimeters Aramis area, and you see similar quite dramatic improvements in the profile temperature And if you look at spatially at where the improvements occur, they're very strongly seen at high latitudes in regions where there's a lot of eddy activity. And there is some minor degradation in the tropical Atlantic and also some parts of the Southern Ocean. But those are regions, the plot is showing percentage RMS improvements. So those are actually regions where the variability, the RMS errors are quite small anyway. But it's something that in the future we might look at trying to resolve. But the general story is that it's a really big improvement. There is a small reduction in the spread of the ensemble, but we think that that's consistent with the improved performance with the new GSI 9 versus the old system. The old system, we started the run with the restart from the old system, so that's why there's that kind of drop. And then we did also manage to do some preliminary runs with the 12th degree systems. As I said, it's very expensive, so this is only for 1 month so far. But we do plan to try to reproduce an equivalent run to confirm that the improvements that we saw with the 1/4 degree carry over to the 12th degree. So the story there is that given the constraints of this particular experiment, it does look like it's showing some similar improvements when you go to hybrid DA with the RMS error. The profile temperature improvements are less, but the period is shorter, so we'd expect that might show bigger improvements with a longer run. So the summary is that we still see a very large benefit when we go from hybrid DA to hybrid DA from 3D VAR at a 1/4 degree. So the RMS error for sea surface height is improved by 20%, about 6% for temperature and salinity, similar to the old version, despite the many updates. So that's really pleasing. I mean, the question that always on my mind is why is that the case? And we think it might be to do with the spatial structures being more congruent with the model. Particularly at high latitude, some of the structures you have the sloping density surfaces, and if the 3D VAR increments tend to be very sort of vertically aligned, perhaps more suitable for the tropics. So that might be the issue, but we do plan to investigate that. We've made it much more efficient, so that's another part of the reason why it's now feasible to go operational. It used to take nearly 2 hours to run the simulation, but it's down to 26 minutes. 12th degree system's working, and it looks like it performs at least as well as a 1/4 degree with similar levels of hybrid DA improvements. We're not planning to run long ensemble forecasts for now. The work's mainly to improve the data simulation, but we will get errors of the day for the first time, which could be very interesting and useful to customers. All being well, this all should go operational early in 2027. So longer term, we're going to have a look at implementing this in the coupled numerical weather prediction system, which we'll be able to do after having gained some additional valuable experience with running this ocean-only ensemble system. And another thing to mention is that I didn't really say anything about sea ice, but that's something that we're going to look at in future as well, because that was the previous work when we looked at the coupled NUP system. We found that had a bigger. The Arctic was a very sensitive area for the atmosphere. So, thank you very much for your attention.
Thank you, Lea, for the Thank you, Dan, for the great presentation. And we get one question from the UPad, but I think she's still writing, from Anthony Weaver. And yeah, so as you mentioned, can you share your screen again, because we can't see your slides?
Oh, okay. All right.
Thanks.
Yeah.
Not yet. I can't see it.
Oh, okay. Sorry, I didn't realize. So I ended the slideshow, but
No, I just read.
but it must have broken the sharing. Apologies. Yeah, I'll just bring it back again.
Okay, so yeah, during this time, I just read the question for you. So, are you retaining the balance operator in the ensemble covariance formulation, or are you using multivariate covariances derived directly from the ensemble?
So at the moment,
your screen.
See, can you see the screen just in case? Can you see anything? It says I'm sharing another application with
we see your screen.
Yes, I can.
Oh, okay. Okay, great. All right. So actually we're retaining the balance operator. We did try. So we did try using the multivariate covariances, and that would seem like it would be a best thing to do. But we was a little bit concerned that the model was getting some temperatures that were not reasonable, you know. So I think the problem, like the ensemble, it's a linear balance, but I think it can obviously, in reality, things are non-linear. So I think that was the reason we were just. It was just that it seemed safer to use the NemoVar balance operator. But I think generally speaking, I think it would be better to use the ensemble covariances if we can do it safely. So it certainly is something that we'd like to try again. And Anthony will know better than me about this actually, but I think that might be more efficient to run as well potentially. But so that would be another advantage to trying that. But I was talking about this mystery as to why the results are improving so much, and I think that looking again at the different options for using the ensemble in NemoVar, that would be a good opportunity as part of that work. And one thing that I wanted to test as well is there's another possibility where you can just use the ensemble variance and length scales. So it'd be interesting to see whether the improvements are similar from doing that to actually using the full sort of structure from the ensemble. So I hope that answers that question.
Thanks.